Okay, yeah, thank you for the invitation. So I'm going to talk about effective limit multiplicities, and I won't write the full title here because I'm going to tell you later what kind of limit multiplicities we're looking at. So I first want to tell you a little bit what limit multiplicities actually are and a little bit about the history before I talk about the special case I'm considering. So the usual setup is that you look at some semi-simple Lie group and its unitary dual G hat. So this will have the Cauchy measure living on it. And you're interested in lattices gamma and the multiplicity of representations m gamma pi of pi, so of some pi, some element in the unitary dual, in the L2, so in the discrete part of the L2 space of G mod gamma. So general setup, and later on in the example I want to consider, this quotient will not be compact, but of course, if this is compact, you will only, you just have an L2 space here. Okay, and so the big question, of course, is what one always wants to know is that how does, okay, so suppose that, okay, you would like to compute this explicitly, but this is very, very difficult. So what one usually does is to ask, okay, so if you cannot compute one quantity explicitly, can we at least understand it on average? So, and what does average mean here in this case? Well, in this case, average means that we take a sequence of lattices n, gamma n, so such that, say, the volume of those quotient spaces goes to infinity. And then you ask, so how does the multiplicity behave as n goes to infinity? So naively, what one expects is that, so if this volume here goes to infinity, in a sense, this quotient here will approximate G. So you could guess that the spectrum of G mod gamma n, in the end, will approximate the unitary dual. So naively, one would expect that if you normalize this multiplicity by the volume of G mod gamma n, that this should converge to the Cauchy measure at pi. So there are problems with this formulation. First of all, this thing here will be non-zero only if pi is discrete series. So for many pi's, this will not really be interesting. Yeah, maybe I should mark this. So this here is non-zero if and only if pi is discrete series. And another thing I should probably emphasize is that this Cauchy measure is actually supported on the tempered part of the unitary dual. So when you look at those limits, you expect that interesting things only happen if you look at subsets of the tempered spectrum. Okay, so let's try to find a more concrete formulation of this expectation here. We'll do this as follows. So better formulation. So we'll define another measure coming, so we have this Plancherel measure, and we define a second measure attached to this gamma n. So mu gamma n living on G hat by putting mu gamma n to be the average G mod gamma n over all pi's. So we just average over the multiplicities, the pi's, which appear here in this discrete spectrum. So you could try to do it for any lattice. The thing is, you don't know it for any lattice, but yeah, so you can. This is something you can write down for any lattice, of course. Yeah. So here, delta pi is just the Dirac measure at pi. Okay, and now what one, of course, would like to say is that this measure here converges to this Plancherel measure. More precisely, so let's put this in very concrete terms. We say that this lattice gamma n, so this family here, has the limit multiplicity property. Or LMP for short, if the following two conditions are satisfied. So first of all, we want that mu gamma n of f converges to the Plancherel measure of f for any smooth and compactly supported function living on the tempered part of the unitary dual. And secondly, as I just told you, the Plancherel measure is only supported on the tempered part, right? So if you evaluate this measure mu gamma n here on a set outside of the tempered part, you expect that it's going to 0 when you want to make sense of this condition here. And this is exactly the second condition here. So mu gamma n, so for any subset A, which is bounded and measurable, mu gamma n of A goes to 0. And so, I mean, people have been looking at those limit multiplicities for a long time, but I think the first people who really made this definition concrete were Fiennes, Lapide, and Müller. I'll mention them again in a second because they proved a very nice example of family of lattices satisfying the limit multiplicity property. Okay, so yeah, let's look maybe at a few examples. Lattices which satisfy this. So I think historically the first examples were towers. So in that case, this family here is just tower of normal subgroups. So maybe let's make this explicit. So in that case, gamma n plus 1 is a normal subgroup of gamma n, and intersection of all those gammas is trivial. And in that case, so, and yeah, you should also probably assume that the gamma n's are torsion-free. But, well, I mean, this is not that important. Okay. In that case, so if those gamma n's are all co-compact in G, so this is, of course, finite index. So if, say, gamma 1 is co-compact in G, then such a tower has a limit multiplicity property. And this is an old result from the 70s, going back to De George and Wallach. And so if, on the other hand, so if, again, if you still have a tower and A is a subset of the discrete series representations, we also know, so regardless of whether gamma 1 is co-compact in G or not, so this also holds just for cofinite lattices. So if you have a set A contained in the discrete series representations, then this property mu gamma n goes to mu L holds as well. So this is due to Wolfs and Spee. I think this is from the 80s. And if the gamma n's are all congruent subgroups in the tower, of course, so again, at the moment we're only talking about towers, so if gamma n are all congruent in gamma 1, of course, then we know that at least for a singleton set, this relation holds. So then mu gamma n of pi goes to mu L of pi. But this is, of course, much weaker than saying that really the measure converges, so the sequence of measures converges. Okay. So another obvious family of lattices are, of course, the family of congruent subgroups in SLN or GLN. So congruent subgroups. And SLN and GLN. And so this is due to Venus, Lapid, and Müller, and another paper by Venus and Lapid. So they take G, so this is quite recently, just a few years ago. So they take G to be SLN or GLN of F tensor R, where F is some number field. And then gamma n, so gamma n, any family of congruent subgroups of SLN OF. Of course, with co-volume going to infinity, right? So with volume of G mod gamma n going to infinity. And so such families satisfy also the limit multiplicity property. Okay, so so one thing you should probably notice is that both of those two cases here, I should also say, okay, so for SL2 this was already, so for SL2R this was already due to Zalmak, I think. So in both cases here, those families of lattices are commensurable with each other, right? And for a long time it was not, I don't think there was any example known of a family of lattices having limit multiplicity property where the lattices are not commensurable with each other. And only recently there were first examples of such cases, namely for G being equal to SL2R and or SL2Z. And in that case, the limit multiplicity actually holds for much more general families of lattices. So I don't want to write down the precise conditions under which it holds, but it includes families which are not commensurable with each other. So should write from quite general families. so including certain non-commensurable ones. And I think there are also at least partly results for SL2R cross SL2R. Okay, so this is also quite recently. And then I should also mention one paper which actually won't be relevant to our example today because it only looks at, or mainly looks at the co-compact case. But there's a paper by 7 people, so yeah, so you also take G to be, yeah, so paper by Aber, Nageron, Iringer, Gelander, and they look at very general sequence, so very general families of co-compact lattices. And so they come from a slightly different perspective. They use something which is called Benjamini-Schramm convergence, which is something quite geometric, so it's not obvious at first that it actually has spectral implications, but they, under certain conditions, they can show that if you have a sequence of lattices, which, or better, if you have a sequence of spaces which Benjamini-Schramm converge to covering space, then they can conclude the limit multiplicities for those lattices. Okay, so I want to talk about basically a more general case of this third category of examples. So we will start with family of number fields. So we'll fix some degree D and R and S, some integers, such that R plus 2S is equal to D. And we look at the family of number fields FRS, which have Archimedean signature RS. So for which this F algebra here is isomorphic to R to the R plus C to the S. And we'll fix such an isomorphism for any N. And the group I want to look at, so this the Lie group G will be SL2 of this algebra here. Okay, mod plus minus 1. So this is not really important, but I want to mod out the center here. The center of SL2. And this is, of course, isomorphic to, we have this fixed isomorphism SL2 F tensor R for any field in this family. And a very natural sequence of lattices to consider here in, of course, the congruence. So, or I only want to talk about the principal congruence. So the principal congruent subgroup of level 1. So SL2OF. So this is, of course, a nice co-finite lattice entry. And yeah, one should of course note that, maybe remark the volume of G mod gamma F. So we'll fix some measure on G here, of course, independently of our F, and well, via this isomorphism, we'll also have some measure on here. So the volume of this here goes to infinity for any sequence of pairwise different lattices in here. Yeah, different fields. And so I usually say that the volume of this just goes to infinity as F varies over this family. And the theorem is now the following, as you can probably expect. So this is from last year, but actually worked on this started working on this much earlier, only published last year. This family here, this gamma F, has a limit multiplicity property. So this doesn't really explain my title, right? So this explains the title of limit multiplicity property, but not the effective. And you can make this actually effective, this property. We need to do a slight reformulation for that. So, in fact, what you can do is you can, so we want to make this a bit more precise. What we can do is we can formulate this limit multiplicity property, this definition, in the following way. So this is a classical way to actually really attack this problem. So this family gamma n has limit multiplicity property if and only if for any smooth and compactly supported function h on G, the mu gamma n of h hat goes to the Cauchy measure of h hat. Where this h hat of pi is just a trace pi of h. So this is, of course, a very convenient way to reformulate this. Okay. And you should maybe also note that this here is actually just h of 1. And so using this formulation, we can give a different version of this, so theorem prime, for any test function h here, and for any positive epsilon. The difference of these two terms here is bounded by some constant times the volume of G mod gamma n minus 1 over 3 plus epsilon. And this implicit constant here will only depend on the degree and our test function h and the epsilon. I'm sorry, it was f, right? So for any f. Okay. So let me tell you a bit about the proof. And as you might have guessed, the proof involves the trace formula. So if you know a little bit about this limit multiplicity, most of the previous works all involve the trace formula in one way or another. The nice thing here in this case is that we actually use a lot of different trace formulas. So we use actually the alpha trace formula for SL2 over F, and so this will vary with F, of course. But because of this isomorphism over there, we can compare those with each other and then can estimate the different terms. And if you were here last week, you saw the trace formula, at least for SL2 over Q, many times. And so in this case, the structure is very similar. So let me give you a few main steps of the proof. So I'll write AF for the ideals of F. And so first of all, what we want to do is, of course, so we want to reformulate this in terms of trace formula. This is a standard step we almost always do. And yeah, so let's define for each of those F's here, we'll define maximal compact subgroup KF in the final part of the ideals by, so this is just product over all places, V, non-Archimedean places of F. Yeah, I should maybe, so G is SL2 for me now. Okay, so maybe I try to write this G bar here to distinguish it from our G over here, but I can't promise that I really keep this throughout. Okay, so this will be G of OFV. Let's write this way. Okay, this is just the usual maximal compact subgroup in the final parts of the ideals. And so then strong approximation gives us that actually we can bring this quotient here into a Delic formulation. So this is just GAF mod KF mod GF. And further, we define one F to be, so this is a function on the finite parts of the ideals. So this is just a characteristic function of this maximal compact subgroup. And then, so what do you want to understand? Well, we want to understand this measure here, right? So this mu gamma f h hat. And we can do this as follows. And for any h, so for any test function on GR, okay, so should we write GFR? We have that this measure here. So I'm not completely precise, right? Because I modded out plus minus 1 in G here from G of F tensor R. So you have to take the average of H times H of minus 1 the argument, right? So this is just the average. But in any case, this will be, so if you multiply this by the volume of G mod gamma F, this will be the So by definition, this is of course just the sum over all pi in G hat of the trace of pi of H, right? Or times the Dirac measure, or if you want, you can just write it as a sum over pi in L2 discrete, G mod gamma n, gamma f. And this is the same as saying, okay, we sum over all pi adelic representations in L2 disk of G A mod G F of the trace of pi of H times this characteristic function. Well, times the volume here, right? So let me write maybe mu f here for the volume, because it will appear several times. But this is, of course, nothing else than the discrete part of, so the contribution of the discrete spectrum to the spectral side of the trace formula. So this is just J disk of H times 1f. Maybe let me write an f here to make sure that it's really, that we view this really as the trace formula for G over f. Okay, so on the other hand, this Poincare measure of H hat is just H evaluated at 1, or better H, since we had to take the average of H of H plus H of minus something. So this is just H of 1 plus H of minus. And so if you multiply this again by the measure here, this is just the contribution from the central conjugacy classes to the geometric set. Okay, so that's great. So we have found the terms we're interested in inside of the trace formula. So what we need to do now is to take the difference and see what survives in the trace formula and how we can bound it. Or in other words, we can say that we need to prove the following. We need to prove, first of all, the geometric limit multiplicity property. When we take the geometric side of f of H kf minus the central contribution, so just this term here, mu f, and maybe also let me write H f little f sub big F here for the test function, times nu f of f of 1 plus f minus 1. And we want to normalize this by the volume mu f. And we'll see that this is actually equal to, what we want to show is that this is bounded just so by some constant which depends only on the degree and epsilon and our h of nu f to the minus 1 over 3 plus epsilon. And I'm sorry, I got a bit mixed up here. So this is, of course, you shouldn't take the volume here. What you want to do is you want to take the volume of the adelic point. So what you do here is you take, is this correct? Yeah, no, this G mod gamma f I should be a bit more careful here because we need to keep track of the maximal compact subgroup here, right? And we need to keep track of the volume of this one because it will really contribute something, some significant volume to this quotient here. So this is the same as say nu f. Let's redefine this nu f times the volume kf. I want to do it. So this is okay. But then this here, just the volume of kf will survive. To the -1, and here as well. And yeah, so this is fine. And here, what we really want is to put mu f to be equal to the volume of GA mod GF. Okay, and if you define it this way, then this is exactly what we want to estimate. And we want to show that this, well, I mean, what we want to show is that this is actually not only bounded by mu f, but we want to show that this is bounded by the volume of G mod gamma. Okay, so and similarly, so we need to prove this effective geometric limit multiplicity property, and similarly we need to prove the effective spectral limit multiplicity. So we need to show that if we subtract the spectral side, so the discrete part from the spectral side, normalize it by the volume, then this will be bounded by the same thing here. And actually, since we divide by, okay, G mod gamma f, so -1/3 plus epsilon. Okay, so this is what we really need to show. And I don't want to say anything, or not really anything, about the spectral side. So I just want to give you a few hints how to attack this geometric limit multiplicity. So the spectral side is actually much easier in this case. So we only look at SL2, so you have very explicit versions for the spectral side available, right? So the only thing, so in fact, basically what survives here is a one-dimensional integral over the trace of some intertwining operator on an Eisenstein series. And what you need to do is you need to look at the normalization of the intertwining operator here, and you will get some logarithmic derivative of some L function. But your L functions here are just L functions of characters, which you can understand very explicitly. So if you analyze this, you can then get such a bound. The geometric side is a bit more difficult. So, I mean, Ali talked about the geometric side a lot last week, and also just in the previous talk. And he explained to you that it's very difficult to compute orbital integrals, right? And those orbital integrals are what you usually see on the geometric side. So I didn't want to do it. So I didn't want to compute orbital integrals. Usually you get very bad bounds. In particular, we not only need to bound here the elliptic orbital integrals, so the regular elliptic ones, which we just saw, but you also need to look at the unipotent contribution from from unipotent elements except for ±1, and also splitting, so split elements, so hyperbolic elements, and the unipotent elements are usually not good are usually very difficult to understand. And so what I did was the following. The second step is to prove the geometric limit multiplicity property. And so let's just write. So this here, let's denote this by geom minus z for geometric minus center. So what you can do is, when Arthur proved different properties of the geometric side of the trace formula, he often approximated the geometric side by a truncated integral over a fundamental domain. And it turns out that this is actually useful in this case. So what you can do is the following. So replace this non-central part here by truncated integrals. So what you do is you take G AF mod GF and truncate it by some t. So t is the truncation parameter. The thing is, you have to take it sufficiently large, and unfortunately, this sufficiently large will depend on your f. So this is a sufficiently large truncation parameter. And then you integrate over the sum of f of x minus 1 gamma x, where gamma runs over elements in GF except for plus minus 1. And so what you can see from Arthur's work is that this geometric side, so this non-central geometric side, will be approximated by this exponentially well. So this is really equal to this up to some e to the minus constant times this truncation parameter. So the thing is, we want to really have an explicit upper bound, right? So we really want to have an effective limit multiplicity. So we need to make sure that we keep track of all constants which might depend on f. And so we need to take care here of this sufficiently large truncation parameter. But it turns out that you can actually, that sufficiently large here is actually not so bad. So we can actually take this to be equal to c times log the discriminant of the field. So it's not too bad, where c is some absolute constant. And this absolute constant only depends on SL2. So and this truncation really happens, I mean, if you think about f equal to q, this truncation really looks like you take the fundamental domain of SL to R. So say in the upper half plane, you just truncate it somewhere here in this case. So there's nothing mysterious going on here. Or you can give a pretty explicit, it's some, so it will be some power of the discriminant times maybe some zeta value of the dedicated zeta function of f. But I mean, this zeta value is harmless, and then you just have some power of those. Okay, right. Yeah. Yeah, let's call this maybe little j t f. So I'm going to need to bound this truncated integral. And if you stare at this a little bit, you will see, I mean, you can of course also see this when you look at the at the fine geometric expansion in terms of orbital integrals, so it doesn't matter. So you don't need to go over to this truncation right now, but you can do it whenever you want. So the next step would be also fine for the geometric part, so not only for this truncated thing. But what you will see is that only finitely many stable conjugacy classes will contribute to this integral. And in fact, you will be able to choose to choose a set of stable conjugacy classes uniform in F in the following sense. So the crucial lemma is the following. There are finitely many polynomials quadratic polynomials say chi1 up to chi(s), coefficients in Q bar. So we consider our number fields to be embedded in Q bar, such that the following holds. If we put, so let's define a set sigma of F. So those will all be gamma in G of gamma F, except for plus minus 1, such that gamma, such as a characteristic polynomial of gamma is contained in this set. You can, of course, also formulate this in terms of this map C, which Ali just used, where you just take the coefficients of this polynomial. And then for any F, this truncated integral here will be equal, well, you still have the truncation. Of the sum of f x to the minus 1 gamma x. But now you sum gamma only over the set sigma here. And maybe I should also remark that, so those polynomials chi1 up to chi(s), they are independent of the field here, but they will depend on the test function h, which we use for the definition of this test function f here. So chi1 up to chi(s) they will depend on h. Okay. And this has, of course, the simple reason that you use the support of your f to pick those polynomials chi1 up to chi(s), right? So, I mean, if you fix one number field f, and then it's, of course, so if you fix this f here, then it's clear that there exists those chi1 up to chi(s). The real assertion of this lemma is that those chi1 up to chi(s) can be chosen independently of your f. So maybe let me just try to give you the idea of the proof in 2 lines. So the idea is the following. So you take, so let's call this map C as before. So C, just take the map from GAF to AF squared, where you send some gamma to the coefficients of its characteristic polynomials. polynomial. And then you look at, say, at C of the conjugacy classes GAF applied to GF, intersected with the support of FF. And so you can, of course, easily see that this will be contained in the intersection of F, or in fact, in the intersection. So I mean, this is just H times 1 KF, right? So that's just the characteristic function of the OF points. So this will be contained in the intersection of OF with a certain compact set. So where BC so this lives in R to the R, say plus C to the S, just considered as a vector space. Oh, sorry. It's just a ball of radius C around 0. And the C will depend on your test function CH, of course. But there will be such a thing. And you and you know that this will be contained in here. And it's clear that for any F, this is a finite set. But you now have to show that this is uniformly bounded. And what you do is you can show there exists a discrete set, lambda. So it's not a lat, it's just a discrete set in here, such that for any F, this intersection is contained in lambda intersected with BC. And this is kind of funny. I mean, it uses some really very nice result of Ellenberg and Venkatesh on the geometry of quadratic forms. So in the end, you will define your lambda here as a union of rings of integers of certain primitive fields up to a certain discriminant. So there will only be finally many of those, and this will prove this the uniform finiteness of this this set here. Okay, I stop here. Thank you. It's just what I get. So I'm not sure if you could improve on it. I don't think so, but I don't know if it's optimal. Maybe you can improve a little bit. Oh yeah, I would like to. I can't at the moment. No, this lemma, you can do this for any n. So this is not a problem. So I'm pretty sure you can actually, I mean, what I do after that is I separate those chi's which are elliptic over F and unipotent and split over F, and treat those different gammas differently actually. And the elliptic part or regular elliptic part I think will still be fine, but I think the unipotent part will give the most trouble.